Welcome to Mysteries of the Universe. I'm your host, Ben Carter, and in today's episode, we travel to the very edge of everything, where space stretches so far it seems to vanish, where the laws of physics tremble at the brink. What happens at the end of the universe? Does it stop, fold in on itself, or does it go on forever? This is the boundary no human has ever reached, and no telescope has ever seen. Yet somehow, we know it is there. In the early 20th century, our understanding of the cosmos changed forever. Before that time, most scientists believed the universe was static and eternal. They imagined a fixed, unchanging structure where the stars were scattered across an infinite sky. But in the year 1929, astronomer Edwin Hubble made a discovery that shattered that idea. By observing the light from distant galaxies, Hubble noticed something astonishing. The farther away a galaxy was, the faster it seemed to be moving away from us. This was not just random motion. It suggested something far more profound, that space itself was expanding. This idea became the foundation of what we now call the Big Bang theory. Rather than a static universe, we now saw the cosmos as a dynamic, growing entity. In this model, the universe began as an unimaginably dense point, roughly 13.8 billion years ago. From that singularity, space expanded in all directions. Not into empty space, but creating space itself. Every galaxy we see today is riding along that expansion. The further out we look, the further back in time we see, because light from distant galaxies takes billions of years to reach us. But this raised a question that no one could easily answer. If the universe is expanding, what is it expanding into? Is there an outer edge to space, like the surface of a balloon being blown up? Is there something beyond the universe, a place where space stops? Or is it more like the balloon itself, with no edge, just curvature that loops back on itself? These questions haunted physicists and philosophers alike. In the decades that followed, telescopes became more powerful. Satellite missions like the Cosmic Background Explorer in 1989 and the Planck spacecraft in 2009 revealed detailed maps of the cosmic microwave background, the faint glow left behind from the early universe. These patterns offered clues not just about the beginning, but about the shape and structure of space itself. And yet, even with all this data, the edge remained elusive. Because the edge of the universe is not a place we can point to. It is not a wall. It is not a line. In fact, it may not be an edge at all, at least not in the way we understand edges. To make sense of this mystery, we must separate what we can see from what actually exists. The observable universe is limited by the speed of light and the age of the cosmos. We can only observe as far as light has had time to travel since the Big Bang. That distance is about 46.5 billion light-years in every direction. That forms a kind of cosmic horizon, a bubble around us that marks the limit of visibility. But that is not the true edge. It is simply the edge of what we can detect. Beyond that horizon, space may continue endlessly, or it may not. This is the puzzle that lies at the heart of cosmology, not just how big the universe is, but whether it has a boundary at all. The observable universe gives us a glimpse into a vast and ancient structure. Within this visible sphere, we see galaxies arranged in complex patterns, filaments, voids, clusters, and walls stretching across unimaginable distances. Astronomers estimate there are more than 2 trillion galaxies within the observable universe alone, each containing billions of stars. But beyond that horizon, where no light has yet reached us, lies a realm we cannot see. And yet, many physicists believe it is still part of the same universe, just hidden beyond the limits of time and light. The key to understanding this lies in the nature of space itself. Space is not just an empty container holding stars and galaxies. It is a fabric, a dynamic, stretching structure governed by the laws of general relativity. When space expands, it is not expanding into something else. Instead, it is space itself that grows, carrying everything within it farther apart. This is why galaxies are not flying through space away from each other. The space between them is literally increasing. This leads to a strange but fundamental truth. There may be regions of the universe that we will never see, not because they do not exist, but because their light will never reach us. The expansion of space can outpace the speed of light, meaning entire galaxies can slip beyond our cosmic horizon. As the universe grows, more of it becomes forever inaccessible, lost beyond a boundary we cannot cross. This is not a physical wall, but a limit of causality, a point past which no signal can ever return. Some scientists refer to this as the cosmological event horizon. It is similar to the horizon of a black hole, not a place you can touch, but a boundary defined by information. Inside the horizon, light can reach us. Beyond it, light will never make it. That means our view of the universe is shrinking in a very specific way. While the observable bubble grows with time, more and more galaxies drift beyond reach, never to be seen again. Telescopes like the James Webb Space Telescope allow us to peer deeper into space and further back in time than ever before. They reveal the earliest galaxies formed just a few 100 million years after the Big Bang. But no matter how powerful our instruments become, they can never show us what lies beyond that cosmic limit. We are trapped within a moving boundary, surrounded by a darkness we can never illuminate. The very concept of an edge becomes more complicated the further we investigate. If the universe is infinite, then there is no edge, only an endless expanse we can never fully chart. But if the universe is finite, it could still be boundless, like the surface of a sphere. A two-dimensional creature living on the surface of a balloon would never find a wall or edge, only curvature. In the same way, space may curve in a higher dimension we cannot perceive, looping back on itself with no boundary, no outside, and no end. And yet the question remains, if there is no edge, then where does the universe stop? Or if it is infinite, how can we ever prove it? What tools, what ideas, what visions will allow us to answer a question that might lie forever beyond our reach? Mainstream cosmology offers several models to explain the structure and possible extent of the universe. These models are grounded in Einstein's general theory of relativity, which describes how matter, energy, space, and time interact. Central to these models is the idea of curvature, the shape of space itself on the largest possible scale. Depending on the total amount of mass and energy in the cosmos, space can be flat, positively curved, or negatively curved. A flat universe behaves much like an infinite sheet. It goes on forever in every direction, with parallel lines never meeting and the internal geometry staying consistent across all regions. Observations of the cosmic microwave background, especially those made by the Planck satellite in the early 21st century, suggest that our universe is astonishingly close to flat. This supports the idea that the universe could be infinite, stretching on without end beyond the observable limits. A positively curved universe, on the other hand, is more like the surface of a sphere. It is finite, but without boundaries. If you could travel in a straight line long enough, you would eventually return to your starting point. In such a model, the universe would have a total volume, but no edge, no outer rim or wall. The entire cosmos would loop back on itself in a higher dimensional form we cannot directly perceive. A negatively curved universe resembles a saddle. It also can be infinite, but its geometry allows for very different large-scale properties. In this model, parallel lines diverge and the universe expands more rapidly. The geometry of this space produces different patterns in the cosmic background radiation, which scientists can compare with observations. What makes the mystery deeper is that current data cannot definitively tell us which of these models is correct. The universe may be infinite, but we cannot observe infinity. The universe may be finite, but so vast that it appears infinite from our limited vantage point. Every telescope, every measurement, every scientific tool we possess is constrained by our position within the observable sphere. One of the most widely accepted ideas in modern cosmology is cosmic inflation, the theory that a fraction of a second after the Big Bang, the universe underwent a brief but staggering expansion. In less than a trillionth of a second, space stretched faster than the speed of light. This rapid expansion would have smoothed out any curvature, making the universe appear flat, even if it were slightly curved overall. Inflation also predicts that the universe is far larger than what we can see, perhaps unimaginably larger. If inflation is correct, then our observable universe may be just a tiny patch within a far greater cosmic structure. The edge we perceive is not the edge of the whole, just the edge of what light can show us. Beyond it may lie more galaxies, more stars, more structures, continuing in every direction. And yet, all of this, every model, every equation, depends on assumptions we cannot verify. We extrapolate from what we see to what we cannot. We infer the infinite from the finite. But whether the universe is truly infinite, or simply enormous, remains an open question, one that may never be answered by observation alone. Even as mainstream theories build an elegant framework for understanding the cosmos, the edges of that framework remain shrouded in uncertainty. Not all data fits neatly within the models. Some observations hint at deep inconsistencies, small anomalies that defy the predictions of even the most carefully constructed theories. These outliers are often dismissed, but they persist. And over time, they have raised uncomfortable questions about the true nature of the universe's edge, if such a thing exists at all. One of the most debated features is the so-called cosmic cold spot, a region in the cosmic microwave background that is significantly colder than surrounding areas. Discovered through data collected by the Wilkinson microwave anisotropy probe, and later confirmed by the Planck mission, this cold spot is not easily explained by standard cosmological models. Some researchers propose that it may be the result of a supervoid, a vast region of space with far less matter than normal, lying between us and that area of the sky. Others have suggested more exotic explanations, including the possibility that the cold spot is a bruise from a collision with another universe. Another puzzle comes from the large-scale structure of the cosmos. The distribution of galaxies across vast distances forms a cosmic web, an intricate pattern of filaments and voids stretching across the sky. Yet some features, such as the Sloan Great Wall or the huge large quasar group, appear so massive that they challenge the assumption of uniformity. According to the cosmological principle, matter should be evenly distributed when viewed on a large enough scale. These enormous structures seem to push the boundaries of that principle, raising the question of whether we are seeing anomalies or glimpses of something beyond. Then there is the issue of cosmic acceleration. In the late 1990s, astronomers measuring distant supernovae discovered that the expansion of the universe was not slowing down as expected. It was speeding up. This led to the introduction of dark energy, a mysterious force believed to make up nearly 70% of the universe. But we do not know what dark energy is. We only know that something is causing space to stretch faster over time. If this acceleration continues, more galaxies will vanish beyond our observable horizon, and the universe will become a darker, lonelier place. But if dark energy changes over time, or behaves differently in distant regions, then the fate of the universe and its possible edge could be far stranger than we imagine. Finally, there are inconsistencies in the measurements of the Hubble constant, the rate at which the universe expands. Different methods of measuring it yield different values, and the disagreement between these results has not been resolved. Some physicists believe this could point to new physics, unknown forces or particles influencing the growth of space. Others argue it may simply be due to unseen variables or limitations in our tools. But the more precise our measurements become, the more persistent the disagreement appears. At the farthest reaches of what we can observe, these discrepancies hint that our grasp of the cosmos and its possible limits may be less complete than we think. Beyond the boundaries of mainstream cosmology, a multitude of speculative and fringe ideas attempt to answer the question of what lies at the edge of the universe. While not widely accepted within the scientific community, these theories persist because they challenge the limits of current understanding. They do not simply stretch the known models, they attempt to rewrite the nature of space, time, and existence itself. One such idea comes from brane cosmology, rooted in string theory. In this framework, our universe is just one three-dimensional slice, or brane, floating within a higher dimensional space. Multiple branes could exist parallel to ours, each containing its own universe. If this theory holds true, then what lies beyond the edge of our universe might not be empty space, but other universes, stacked or layered alongside our own. Collisions between these branes could even be responsible for cosmic events like the Big Bang. In that view, the edge of our universe may simply be the beginning of another. Another speculative concept involves bubble universes, The idea that during cosmic inflation, multiple regions of space-time could have inflated independently, forming self-contained bubbles. Each bubble could have its own physical laws, constants, and dimensions. Our universe would be just one among many, adrift in a cosmic foam of universes. The boundaries of these bubbles might occasionally brush against one another, leaving faint traces, perhaps in the form of unexplained patterns in the cosmic background radiation. If such collisions occurred, they would mean the universe does have an edge, not in the traditional sense, but in the form of a membrane separating it from other realms. Then there is the idea that the universe is finite but bounded by something fundamentally different, not more space, but a limit of information. Some physicists have proposed that the universe operates like a vast quantum system, where space and time emerge from a deeper, non-spatial reality. In this scenario, the edge of the universe might not be a place at all, but a phase boundary, where classical physics dissolves into a more fundamental quantum structure. What lies beyond may not be something we can ever observe, because it would not be subject to space or time. Even more radical theories propose that the universe is a simulation. In this view, what we perceive as space and expansion is part of a programmed reality. The edge would be the boundary of the simulation itself, an artificial limit beyond which nothing exists. This idea is untestable, at least with current tools, but it continues to gain traction in both scientific and philosophical circles. If true, it would mean that the universe ends not with a physical boundary, but with the edges of code, a digital silence where reality is no longer rendered. Each of these ideas offers a different vision of what might lie beyond. They differ in mechanisms, dimensions, and implications. But they share one thing in common: the belief that the universe, as vast and strange as it is, may only be part of a much greater whole, a greater reality that cannot yet be seen, but that might someday be inferred through patterns, distortions, or mathematical fingerprints hiding in the deepest background of space. As these speculative frameworks expand the boundaries of science, they inevitably invite deeper questions, not just about the mechanics of space, but about meaning. What does it imply if the universe has no edge? Or if it does, and that edge is unreachable, unknowable, or governed by principles beyond human comprehension? These mysteries push us toward not only physics, but philosophy, spirituality, and the symbolic mind. Throughout human history, cultures have pondered what lies beyond the visible heavens. Ancient Mesopotamians believed the sky was a dome resting on cosmic waters. The Egyptians imagined the stars as lights carried by gods in boats across the sky. Even early Greek philosophers such as Anaximander spoke of the infinite, not as a measurable distance, but as a principle, an origin without end. These ideas were not scientific in the modern sense, but they reflected an intuition. That the universe has structure, purpose, and perhaps boundaries beyond the reach of the senses. In many spiritual traditions, the edge of the known world was a gateway to the divine. The heavens were not merely far away, they were realms of higher order. To cross into them was to move beyond the material, into the sacred. Today, science seeks data rather than destiny, but the drive remains the same: to understand what lies just beyond the veil of experience. In recent decades, philosophers of mind and consciousness have entered the cosmic conversation. Some suggest that space itself might be linked to awareness, that the structure of the universe is not merely physical, but informational. If consciousness is somehow woven into the fabric of reality, then the edge of the universe may also mark a boundary between experience and the unexperienced, between being and the unknown. Even within modern science, there is acknowledgement of a limit, a horizon not just of visibility but of knowability. The anthropic principle, for example, suggests that we observe the universe the way it is because we are here to observe it. If the universe were different, we would not exist to ask the question. This raises a strange mirror, that the observer shapes what can be observed, and that the edge of the universe is also the edge of our own comprehension. Symbolically, the edge of the universe may represent something deeply human, the limit of mortality, the brink of understanding, the confrontation with the infinite. Whether it is a wall, a horizon, or an illusion, it draws us to imagine more. It reflects our hunger for meaning, for answers, for orientation in the face of cosmic scale. And in that sense, the question of the universe's edge is not only a matter of astrophysics, it is a question about the structure of reality itself. What does it mean to live in a universe that may be infinite, or finite but unbounded, or part of a multiverse, or encoded in quantum data, or simply a product of our own perception? Every possibility changes how we see ourselves, not just where we are, but who we are, and why this cosmos is the way it is. As we piece together everything known and imagined about the universe's edge, certain patterns begin to emerge, not in physical space, but in the way knowledge itself unfolds. The more we learn, the more we realize how much remains hidden. Every measurement pushes the boundaries of detection. Every discovery deepens the questions. The edge is not just a destination we approach, it is a shifting frontier, always receding, always beyond. Let us consider the core elements. The observable universe is bounded by time and light. It forms a sphere about 93 billion light-years across, centered on the observer. But that edge is not fixed. It grows as time passes and as light from farther galaxies arrives. Yet even that expansion is partial. Galaxies too far away are receding faster than light due to the acceleration of space. Their signals will never reach us. They have already crossed a horizon beyond which no communication is possible. We know that space is expanding. We know that this expansion is accelerating. We know that the universe appears flat on large scales. These are not theories, they are measurements, confirmed repeatedly by missions such as the Hubble Space Telescope, the Sloan Digital Sky Survey, and the Planck Observatory. The structure of the cosmic web, the isotropy of the microwave background, and the uniformity of galactic distribution all point to a universe with no edge in the traditional sense. And yet, that very conclusion is a boundary, a philosophical one. A wall of knowledge formed not by stone, but by data. We know that the expansion may continue forever. We know that beyond our light horizon may lie more galaxies, identical or vastly different. We cannot say whether the laws of physics hold there. We cannot know whether matter clumps into stars and planets, or whether conditions vary in ways that defy everything we assume. We know there are anomalies, cold spots, discrepancies in expansion rate, unexpected alignments, vast structures that stretch across hundreds of millions of light-years. Each one challenges the tidy models. Each one suggests there may be more than we understand. We have seen the edge of what light allows. But what about gravity? Gravitational waves, ripples in space-time itself, can move through regions long before light arrives. Could they reveal structures beyond our horizon? Could future detectors give us insight into the unreachable? And what of neutrinos, the ghost particles that slip through matter and space nearly undisturbed? Could they carry information from realms we cannot see? We are now building telescopes that look not just across distance, but across time. Instruments that capture the faintest background signals from the early universe. Missions like the Nancy Grace Roman Space Telescope and the European Space Agency's Euclid mission may help refine our models of expansion, structure, and cosmic geometry. But even as our reach expands, the edge continues to stretch ahead. It is not a destination. It is a moving target, a boundary drawn by what is possible, not by what is there. And in that sense, the edge of the universe may be the purest form of mystery, a horizon we can describe, but never cross. As we draw together the clues, theories, and observations, the nature of the universe's edge becomes not clearer, but more profound. The sum of what we know outlines a boundary not of walls, but of understanding. It is the edge of light, the edge of time, the edge of theory. We are surrounded not by emptiness, but by a deep, structured silence, filled with galaxies we will never see and forces we may never fully explain. The cosmic microwave background, the afterglow of the Big Bang, forms a kind of visible shell around us. It is the most distant light we can detect, coming from a time when the universe was only 380,000 years old. Beyond that, space was too hot and dense for light to travel freely. The moment this light was released marks a limit, a fog beyond which direct observation is impossible. Yet even that wall is not fixed. The photons that make up the background continue to stretch as the universe expands, cooling and shifting toward lower energies. Everything we observe, galaxies, quasars, clusters, sits inside that bubble. The shape of the background, its minute variations in temperature and density, reveals the early conditions of the cosmos. But it also raises deeper questions. Are those patterns just fluctuations in matter and energy? Or are they the fingerprints of something larger? Something pressing against our universe from beyond? Theoretical physicists often speak of initial conditions, the set of properties that define the universe at its beginning. But if space and time themselves were created at the Big Bang, what determined those conditions? Was there something before? Is our universe one outcome among many? Or was it inevitable, the only configuration that could exist under a deeper law we have not yet discovered? Some believe the edge of the universe is defined not by what we can measure, but by what we can imagine. In that view, each new equation, each new model, expands our mental horizon. The edge shifts not when a telescope sees farther, but when thought reaches further. In this way, physics and philosophy become indistinguishable. Others suggest that the edge is an illusion, a trick of limited perception. Just as the horizon at sea appears to be an edge, but is only a limit imposed by curvature, the cosmic horizon may be a limit imposed by our own condition, embedded within space, dependent on light, bound by time. And if that is true, then perhaps there is no final answer. No moment when the edge will be reached and the mystery resolved. The search itself may be the point, not the destination, but the unfolding of ever deeper understanding. The edge of the universe may be the edge of consciousness itself, a meeting place between what is known and what remains forever beyond reach. In the end, the edge of the universe remains one of the most elusive concepts in all of science, not because it hides behind clouds or distance, but because it may not exist in any form we can define. We imagine borders, we think in terms of inside and outside, of beginning and end. But the cosmos does not follow those rules. It unfolds on its own terms, governed by forces we are only beginning to understand, and dimensions we may never fully grasp. We have peered across space and time, mapped the afterglow of creation, and traced the slow drift of galaxies as they vanish into the dark. We have asked whether space is infinite, whether it wraps around itself, or whether it is one small fragment of a far larger whole. And in every direction we look, the message is the same. There is more, always more. More to see, more to question, more to imagine. Perhaps the most haunting idea is that the universe has no edge because there is no outside. That everything which exists is already contained within it, not just matter and energy, but thought, awareness, and possibility. In this vision, the universe is not a container, but a process. A living, evolving structure of complexity, governed by principles that include observers like us. Or perhaps the universe does end somewhere far beyond the reach of light and gravity. A wall of physics, a membrane, a place where space folds inward or dissolves into something else. If that is true, then we may never know, because every step toward the edge is also a step forward in time, and the edge moves as we move. And maybe that is the point. The edge of the universe is not meant to be reached. It is meant to remind us that we are part of something vast, something ancient and expanding, filled with secrets we have not yet earned the tools to decode. It asks us to be patient, to wonder, to look up and keep looking, even when the sky answers only with silence. Because within that silence lives a truth older than stars. That the universe does not need to be understood to be beautiful, and that even in the face of infinite mystery, we can still ask questions. We can still imagine the edge even if we never find it. And in doing so, we become part of the very mystery we seek to explain. Thanks for listening. This has been Mysteries of the Universe. If you enjoyed today's episode, be sure to follow us wherever you get your podcasts. And if you'd like to support the show and unlock bonus content, subscribe to the Forbidden Knowledge Network on Patreon. Subscribe now.